The second problem I want to do, I'm not going to solve the whole problem in full detail, but I want to show you how you can apply the same techniques I showed you in the first problem to one with slightly more difficult geometry and one that you haven't seen before in your homework. So this is problem 5, 147 in the 8th edition of Merriam, Craig and Bolton. We have a square plate controlled by two pivoted links, OA and BC. Link OA has a constant angular velocity. For this instant that's represented, we're told the angle theta, and we're told AB is parallel to the x-axis. For this instant, determine the angular acceleration of the plate and of link CB. So let me start to draw this. Here I have the plate. I'm going to have to pay some attention to the geometry here. I'm going to have to work out the geometry. The plate has sides of length 160 millimeters. Here's point B on the plate, point A on the plate. Point B is connected by a link to point C. We know the length of that link is 200 millimeters. We know this angle is 4/3, so that's helpful. That tells us we're in a nice 3, 4, 5 triangle. So the opposite side is opposite over adjacent. The opposite side is bigger, so this is 160, this is 120. Let's just check that that makes sense. Tan of theta is 160 over 120, that's 4/3. 4 squared plus 3 squared equals 5 squared. Okay. So this distance here, I can see is going to be 40 millimeters. Okay, then here we have another 80 millimeters, and that lines up with the line on which point O goes. Point O is 220 millimeters, so that will be 160, that will be 60. There's point O. OA are connected there. We know point OA is 100 millimeters long. We don't know the angle. Let's sketch it in there as beta of the link OA. We'll be able to work it out. Is going to be opposite 80 millimeters over 60 millimeters. Oh, aren't we lucky? It's also a 4/3 triangle. So in fact, beta is equal to theta. That seems fortunate. In real life, triangles usually don't work out like this, but in the textbook, triangles often are 3, 4, 5 or 30-degree or 45-degree triangles because we don't want to spend all our time doing maths. Okay, so we've got the geometry nailed down. So this here is point C, that there is point O. We are told that OA has, at this instant, a constant angular velocity. So omega OA equals 4. Constant means that link is not accelerating. Alpha OA equals 0. Which direction is it moving? It's moving clockwise. So if I write it as a vector, that's minus 4k radians per second. Okay, I am looking for alpha AB and alpha CB. So I'm going to solve a relative acceleration problem. I'm going to write this the other way around. I know AA, I'm going to write AB B equals AA plus AB relative to A. Once we're talking about accelerations, remember that acceleration can be broken into normal and tangential components. The normal component is minus omega cross r, and the tangential component is alpha cross r. For the case of rigid body rotation in a plane, which are all the problems we are dealing with in Chapter 5, I can express this more simply as minus omega squared r. Notice this is a scalar, so it's just the magnitude of the angular velocity, r plus alpha cross r. And if you want to know how exactly this is true, you should go check in the supplementary notes this derivation that proves this is given in the supplementary notes. Okay, so each component, each acceleration in this relative acceleration equation has two components. AB normal plus AB tangential equals AA normal plus AA tangential plus AB relative to A normal plus AB relative to A tangential. Okay, and which ones do we know? We have been told omega OA. So we know AA normal, magnitude and direction. We have been told that alpha OA is equal to 0, so we know AA tangential is 0. That still leaves us with 4 vectors. We will be able to work out the direction for each of them, but we don't know the magnitude. This is only 2 equations. I cannot solve for 4 unknowns with 2 equations. What do we do now? Well, remember that the normal components of acceleration come from the angular velocity. So, if I solve the relative velocity problem and find omega BC and omega AB, then I will know these 2 components and I will be left with 2 unknown components. So, the first rule of solving relative acceleration problems is we always start by solving for the velocities. In some cases, you're given all of the velocities, then you don't need to go through this step. But you should always start the problem by thinking, I need to know what the velocities are before I can solve for the accelerations. Okay, let's write the relative velocity equation. VB equals VA plus VB relative to A. I know VA. I'm looking for VB and VB relative to A, and when I find them, I will have found omega BC and omega AB. So just like we did in the previous problem, let's start by identifying in which direction things are moving. Which direction is point A moving? The velocity of point A is moving perpendicular to this arm OA. A can only move in a circle around point A, so instantaneously the motion is tangent to the arm OA. We know it is moving down because we've been told the direction of omega OA, so this is VA. VB, and let me just go ahead and fill in that angle. This angle is beta, this is 90 minus beta, this is beta, but we've said beta is equal to theta. VB is moving in a circle around C, so it is perpendicular to BC. Sorry, I don't know the direction. Take off that head. It might be moving, depending on whether BC is rotating clockwise or counterclockwise, it might be moving up or down. This is the direction of VB. This angle is theta. This is 90 minus theta. This angle is theta, so this angle here is 90 minus theta. V of B relative to A, we pretend point A is fixed. Relative to this pretend fixed point A, B must be moving vertically. So if I come and do the two sides of my equation, start with what I know. I know VA is moving down at an angle of theta below the horizontal. I know VB relative to A is vertical. I come back to this side. I know VB is moving at an angle of 90 degrees minus theta below the horizontal. It turns out to actually be, if this angle is 90 degrees minus theta, then this angle must be a right angle. So VB is moving like this. The way to close the triangle is up here. We have fortuitously ended up again with a 90-degree triangle. This angle here is theta. Is that angle theta? No, this angle here. I'm confusing myself. In this triangle here, this is theta, this is 90 degrees minus theta. So this angle here is theta. That makes more sense. Okay, so either using the geometry or the algebra, we can solve for omega BC and omega AB.